sure that everybody got a chance to finish off the experiment where we were looking at the densities of different igneous rocks. We wanted to try and use this information to see if we can see any link between oceanic crust and continental crust. So we've got 4 rock samples. We've got a granite, we've got a basalt, we've got an obsidian, and we've also got a little bit of pumice. Now the problem with these is they're not all the same shape or size, and so therefore, even if I weigh them all, that's not going to give me all the information I need. I actually need to calculate difference in the density. In order to calculate the density, I need to divide the mass by the volume. So I can get the masses fairly easily just with an electronic balance like this one. Okay, so I'm going to pop it down because I don't want to be measuring things in midair. So I'm going to pop it down, make sure I tar it. So it goes back to 0, and I'll start with my piece of granite. Of course, it's important that you make sure that you keep all of these the same as you're doing this. So for my granite, the value that I have is 40.40 grams. So the next one I'll weigh is my piece of basalt. Maybe I'll bring this down a little bit so you can kind of see what's going on here. So here's the piece of basalt, and this one has a mass of 12.04 grams. So you can already see there's a big difference in the masses, but I would expect that because they're different size rocks. This is the obsidian. Just re-zero that. And for obsidian, I have 15.62 grams. And then my last one is my little piece of pumice. And it's coming in at 4.49 grams. Now, what I need to do next is I need the volumes. Because these are not regular shapes, that makes it a little bit tricky. So what I'm going to have to do is I am going to have to use Archimedes' principle of displacement in order to determine exactly how much, what volume each of these takes up. So in order to do that, I'm going to move the computer over a little bit to the edge of the sink. And I'm going to use one of these. This is a Eureka cup. You can see that there's a hole. Maybe you can see, yeah, there's a little hole there, which the water can drain out of. And if I fill it with water, it'll reach a point where water will start to come out of that little hole. You can see it now. So I'm going to just sit that on the edge of my sink. Just let that drip for a little bit and until it's not dripping anymore. Then what I can do is I can place underneath that a measuring cylinder. Now I do have a large measuring cylinder here, but I can get a smaller one if I think that the displacement is going to be hard to read on something like this. But let me just start with the granite first of all. So I'm going to pop that in underneath, and then I'm going to drop my granite in. What you can see is that the water has risen, which means it's come out of the little tube. And if I've got everything out, then I should be able to read my value. So again, we look at the bottom of the meniscus, and you also need to look at them straight on. So I'll have a look at that. So I'm looking at about 13 mils for that one. So I'm going to pour the water out of both. I'm going to recover my rock sample, and I'm going to repeat that process 3 more times. Now the amount of water that's come out when I've dropped the basalt in is so small that I'm not going to be able to read it with my measuring cylinder. So I'm going to need to transfer it to a smaller measuring cylinder. So let's do that here. Okay, so now I can read a little bit more accurately what this value is for the basalt. Let's bang on 2 mils. Okay, so 2 more. This time the obsidian. So you can see this one again is under 10 mils, and it's sitting from where I can see it's sort of looking like about 7.6, but let me just double check that. 7 to 4, maybe 7.5. Now my last one's going to be tricky because one of the things with the 3 that I've looked at so far is that they are all denser than water. So therefore they all sink when I put them into the water. The pumice I might have a bit of a problem with because pumice may float. And if the pumice floats, then I'm going to have to try and make sure that all of the pumice sits underneath, or else I have to try and work out how much of the pumice is sitting above it. So we'll try this one and we'll see how we go. A little more difficult with that one, but then I've got a little reading here, so I'm just going to transfer that over. Okay, that's my experiment concluded. What I need to do now is recover all of these samples and then put the results together. So I'm going to turn this computer off now and we'll welcome back. Now we've got the opportunity to put those results together and see if we can tell any story from them. So what we'll do is we'll fill this sheet out together. The mass of the granite was 40.4. The mass of the basalt was 12.04. For the obsidian, it was 15.62. And for the pumice, 4.49. Now, when I used the displacement method for the volumes, I got 13 mils, and I got 2 mils, and I got 7.5 mils, and I got 1 mil. Now what we want to do with each of these is we actually want to do a calculation. And in order for us to do a calculation, what we need to do is we need to know that the density can be found by dividing the mass by the volume. So the density, therefore, of my granite I can find by dividing the mass of the granite, which is 40.4, by 13. Now, when I do that, I get a value of, we can do it, and one of the advantages of doing it in Excel is you can set formulas into Excel that make it an automatic process. So I'm going to have B2, which is the mass of the granite, and I'm going to divide that by C2, which is the volume of the granite, and that should give me the density. Now, obviously, there's lots and lots of decimal places here, and we don't want those, so we probably want to just go back and remove some of those decimal places. Maybe get down to 3.11 is fine. So 3.11 as a density. From my knowledge of granite, that seems a little on the high side, but let's have a look at some of these other results and see if we can compare them. So I'm going to save a little bit of trouble by just turning this into a little plus sign and dragging it down. And when I do that, what it'll do is it'll bring the formula down into each one. So what you can see is 6 for the basalt, 2 for the obsidian, and 4 for the pumice. Now there's some interesting things that have happened here. And one of the things when you're using the Eureka cups is that it's hard to get that water in exactly the right spot. If you have lost too much water, then obviously some of the water is going to rise before it starts to pour out of that little funnel, which means that we're not going to get as much as we would expect. And I have to say, especially granite I thought was a little bit high. This value for basalt seems ridiculously high. I would expect it to probably be closer to half of that. However, having said that, you can see that there is a difference between granite and basalt, and that is one of the things that we did want to have a bit of a look at. The obsidian is probably closer to the value I would expect for obsidian, probably around 2.5. The interesting thing about obsidian and pumice is these are amorphous. They cool so quickly from extruded volcanic or igneous rock that the crystals don't have time to form. So obsidian is volcanic glass, so it's no crystalline structure in there. And the pumice is actually, generally speaking, it's made from, think about what happens to soft drink. If you shake it, you get it really frothy. Pumice is often made from that kind of froth where you have lots of gases, lots of bubbling happening, and then it solidifies that way. That being said, what we generally find happening with pumice is pumice floats on water. And I'm sure you've seen specimens of pumice before. You may have also heard the little clink when I dropped the pumice in. I certainly wasn't expecting it to drop to the bottom. So I suspect that my pumice is mislabeled. So I would have a question mark about that. And of course, if I said to you, what would you do with these results? Hopefully the first thing you would do is say, well, I'd repeat them, especially if there's some values in there that you feel that you're a little concerned about. And we can also compare these with the book values. So we can get Google out, have a look at our textbook and see if these values actually agree with the ones that are listed in the textbooks and the references. The one thing that is very clear, and the one pattern that hopefully we can link into our work with plate tectonics, is this. We know that when ocean crust is moving in one direction, it meets continental crust moving in the opposite direction. We end up with a subduction zone, and we end up with a subduction zone because the oceanic crust goes under the continental crust. So the subduction zone is created basically with this dipping down of the oceanic crust. The reason it does that is because it has a higher density. The continental crust has a lower density. Now, given these two amorphous ones that we'll kind of leave out for now, if I was to ask you which of these two rock types would you consider to be more characteristic of continental crust and which one's more characteristic of oceanic crust, hopefully you would say, well, if it's a higher density, then that means the basalt is more likely to be a major component of oceanic crust, whereas the granite is more likely to be a component of continental crust. So there's a little conclusion that we can put together for our results that hopefully will give you a bit of a story that you can tell from the results that you've gained. Remember, the thing with science is one of the reasons we keep repeating our science is because it's very important that we continue to ensure that we have good, reliable results and that we develop validity. And sometimes with rock samples, one of the simple mistakes that we can make is in their identification. So I'm going to go back and have another look at the pumice and see if I can find a slightly different story. As I say, I'd be expecting a density much lower than 1, certainly not something that's going to go clunk on the bottom of the can. But these other results give us a nice little trend. The numbers are much different. I would expect basalt to be closer to a 3 and granite to be closer to, say, a 2.6, 2.7. But they give you a bit of an indication of the difference between them. Definitely basalt is the more dense rock, and it's the one that's more likely to be a component of oceanic crust. Thanks for watching.